And welcome to class 1 of ATMO 620. This is actually more like class 0 as we discussed the other time. I would like to take this class as an opportunity not so much to start with the material, but to go over some basic math that we will be using throughout the entire class. Now, this is not meant to make you feel bad or, to shame you if you don't know some of the material or some of the math that I'll talk about for this class. But it's really just to check that we're all on the same page as long as math is concerned. That we all understand the basic material. If some of the stuff that I'm gonna talk about is new to you, no problem. Don't worry. Just contact me and we can discuss a plan. I can explain some things if they're obscure and whatnot. This is the very first time that I teach in this format. And so please let me know if some things could be done better, if there's something that you don't particularly like, etc. And when I say in this format, I say using this sort of drawing pad arrangement as a sort of a whiteboard, if you will. So please bear with me. I'm not entirely familiar with with how this machinery works, but hopefully it won't be too bad. Okay, so without further ado, let's just start and discuss the math that we'll be using. I'm sure that you're all familiar with what a derivative is, but let's start simple and let's start with the definition of a derivative and what that actually is. So we will start assuming that we have a function f of x, where x is some real number, okay? And by definition, the derivative of f of x, which is typically indicated with a prime, okay? The derivative of f of x is defined as the limit for h that goes to 0 of f of x plus h minus f of x divided by h. This is probably something that you've been seeing from high school, but again, it's always good to go back to the very basics. And this is actually, apart from the definition, this also gives you a recipe to compute a derivative. So if you want to compute, if your f of x, for example, is x squared, okay, the function that takes a value and squares it, then by definition, your f prime will be x plus h squared minus x squared divided by h. This you can expand and it becomes x squared plus 2x h plus h squared minus x squared divided by h. Now these two cancel out, and so what you're left with is 2x plus h. However, we're taking the limit here, so h goes to 0, and you're left with 2x. Okay, so derivative of x squared is generally 2x for any x. Okay, so this actually gives you some kind of a recipe and a way to compute a derivative. Notice that by the way it's defined, this also gives you a nice geometrical interpretation. So if you have a graph like this, this is your x, this is your y-axis. Let's say that f is some weird function, not better defined. Now, let's say you're at point x0 here, okay? This is x0 plus h. Okay, so this is f x 0, and this is f x 0 plus h. Now, this difference between f x 0 plus h and this difference are the two terms involved in the derivative. So the derivative of f will be this distance here divided by this distance here. So this is the geometrical interpretation of the derivative. Now, the derivative enjoys a number of important properties that we need to keep in mind. So if you have the derivative of the product of two functions, so let's say that h is the product of two functions f and g, the derivative of h is the derivative of the product f times g prime. This is the derivative of f times g plus f times the derivative of g. Okay, let's write the prime. Okay, this is called the product rule, and we will use it and we will see it a number of times throughout the class. The other thing is the so-called chain rule. So for example, if f of x is the function of a function of x, okay, then f prime, write it down here, is h prime g of x, close both parentheses, times g prime of x. Okay, this is also known as the chain rule. Chain rule. Okay, excellent. Now notice that we have been using, so far we have defined the derivative in one dimension. So x belongs to r, and r is just the real line, okay, this real line here. But obviously we can define functions in multiple dimensions. So for example, let me erase the screen here. So in the new screen we can talk about functions defined in higher dimensions. So we said if you have a function f of x where x is in the real line, then we know how to define a derivative. However, this needn't be the case. X can be a vector in a multidimensional space, so we will indicate it with an arrow like this. This would be x1 down to xn, and this will belong to some multidimensional space. It could be where n could be any number. In this case, we can still talk about derivatives, and in particular, derivatives here will be called gradients. Okay, so the gradient of n of f, of this vector x will be a vector itself defined in the sort of multidimensional space Rn, okay, and it'll be a vector of derivative. Derivative of f with respect to x1, derivative of x with respect to x2, and so forth, all the way down to the derivative of f with respect to xn. Okay, very good. Okay, so one thing that derivatives are useful for a number of things, but one thing that we will see quite often where derivatives are used is what we call a Taylor series or a Taylor expansion. Now, these series are defined formally, and we'll see in a moment how, And essentially, they provide a representation of a function as a sum of many terms, of an infinite amount of terms. So the Taylor series of the function f of x is defined as the sum for n that goes from 0 to infinity of the nth derivative of x computed at point x0 times x minus x0 to the nth power divided by n factorial. Now, what is the nth derivative? Well, we've seen the first derivative f prime of a function. Just like you define f prime, you can define the derivative of a derivative, the derivative of a derivative of a derivative, and so on. So the nth derivative of a function is the derivative of the derivative of a derivative, and so forth, n times. And x0 here is some point that you have fixed somewhere. And x minus x0, you want it to be a small enough quantity, if you will. So this is a handy way to represent functions sometimes, because functions are very complicated. Functions can be nonlinear, and they can make things extremely hard and extremely awkward. But you can, if you are at a particular point at 0, if you go to a point nearby, as long as you're nearby, then you can write the function in much nicer ways, if you will. I'll give you an example of this expansion. Suppose you have the function 1 over 1 minus x. Now, this is a nonlinear, apparently complicated function. Now, if you do all this calculation, and if you take x0 to be 0, then this, you can write it as 1 plus x squared plus x cubed, x to the third power, or x cubed, plus x to the fourth power, and so on. You get the gist, okay? And so, provided that x is small enough that you're close enough to 0, then all these terms, the power of a small number is an even smaller number, and so all these terms can be neglected. Okay, we can pretend they're not there, and so you can approximate 1 over 1 minus x, which is a complicated function. You can simply approximate it as 1 plus x, which is simple enough to write down. Let me write down again. Other important, using the definition of the Taylor series, which I deleted, so I'll just write it here again. F of x equals to sum for n goes from 0 to infinity of the nth derivative point x0 over n factorial times x minus x0 to the nth power. Then, for example, e of x, the exponential function. This you can compute, you can compute the nth derivatives. Now, the derivative of the exponential is the exponential function, and this is the only function that enjoys this property. And so this, by definition, let's take again, for simplicity, x0 equal to 0. The derivative of the exponential is the exponential. And so if you evaluate it at x0 equals to 0, e to the 0th power is 1. And so you can see that this can be simply written as the sum for n that goes from 0 to infinity of x to the nth power divided by n factorial. What does that look like? Well, that's going to look like, 1 plus x, now plus x squared over 2 plus x cubed over 6, and so forth. So once again, if you're close enough to 0, then these terms are small enough that can be neglected. And so once again, you can approximate e to the x with 1 plus x. This isn't usually the case that you can approximate with always with 1 plus x. There are other cases where the approximation may be different. For example, if you were to take the cosine of x, if you were to do the calculation, this would be, you'd find that this is equal to 1 minus x squared over 2 plus x to the 4 factorial, which is 24, plus x to the 6, this is minus x to the 6 over 6 factorial, and so forth. Okay, so provided that provided that you're close enough to 0, in this case, the approximation that you can use, the leading order approximation that you can use is 1 minus x squared over 2. These terms would come into play if you were to be interested in higher order corrections, but the first terms that you want to care about are these two guys. Sine of x, just because we're talking about trigonometry, sine of x, you can do the whole calculation, and you'd find that this would be x minus x cubed over 3 factorial plus x to the 5th power over 5 factorial minus x to the 7th power over 7 factorial, and so forth. I'm not going to go through all the through all the possible Taylor expansions because there's literally infinitely many. But just know that whenever you have an even very complicated looking function and you have to deal with this function, maybe you have to plug it in into some weird complicated equation and you don't know how to get out of it, sometimes you can simplify this function. You can simplify this function provided that you make small enough movements on this function that you can approximate it as a line or a parabola, much simpler powers to deal with. And essentially, if you're still wondering what the Taylor series is, well, the Taylor series, you could think of it as a way to represent a function. So if I give you the function e of x, okay, this is one way to represent it, to write it like this, okay? Another way to represent it would be geometrically. If you write down the axis, this is the x-axis, this is the y-axis. Another representation. My pen is very unhappy whenever I do certain strokes. Anyway, this is another way of representing the exponential function, to represent it graphically. Another way is to say that the exponential function is that function that is equal to its derivative, because the derivative of e of x is e of x again. And so there are many ways of representing functions, much like there are many ways of representing numbers. So if I give you a particular number like, 24, okay, I would immediately write down 24, but this is not the number. This is a representation of the number, okay? I'm using base 10 to represent this number. This says 20 units, this says 4 units, 10 to the 0, plus 2 units of 10 to the 1. So in base 10, this is a way to represent 24. But it's not the only way to represent the number. if you were to point me to 24 tables, that would be another representation of the number. If you were to represent this number in, I don't know, base 4, for example, this number would look completely different. And so we can choose how we represent numbers, and in the same way, we can choose how we represent functions, okay? And maybe sometimes 24 is too much to deal with, and maybe sometimes 24 can be approximated as 25, which is a perfect square, which is kind of similar to this idea, right? Where you say, oh, let's say that we move only a little bit, then the function looks like that. And much in the same way, you can say, well, okay, let's move a little bit away from 24, and we get a number that has, different kinds of properties that is similar enough to 24, okay? I hope this doesn't sound too confusing, but just to give you an idea that the way we think of functions and the way we think of numbers is very much representation dependent, and functions and numbers are actually something a lot deeper than our representations of them. And so you shouldn't feel bound to one particular way of representing something. And in certain occasions, it may be better to represent things in a different way. Another thing, we will not be using this extensively, and I will not spend too much time on this, but another way to represent functions over a particular interval, let me erase all this, is through a so-called Fourier series or Fourier expansion. It takes the name from a French guy called Fourier. We will see this guy later on in the class because he was, a mathematician, a natural philosopher, what have you, and he was involved in he played some part in the in the discovery of greenhouse gases. So we'll see this name later. We'll see him when we'll talk about thermodynamics because, he's done so many things. But one of the things he's done is that he said, well, if you have a certain function, okay, a well-behaved function, and we consider this function over a particular interval, okay, this is x, and this is y again, and this is some function f, and we'll take it over some interval of length L, okay? Then he says this function, whatever it is, can be written in the following way. F of x can be written as some constant term a0 divided by 2 plus and sum that goes from 1 to n of the following: a coefficient a of n times the cosine function of 2 pi. 2 pi's are always involved when we talk about trigonometry stuff, times n times x divided by the length of the interval L, plus some other coefficient that we'll call b of n times the sine now of 2 times pi times n times x over L, okay, the length of the interval. And Fourier gave some recipe to compute a0, to compute an, and to compute bn. Now, there is no need to go into too much detail with this. We're not going to use this, but just to give you a flavor of the fact that there's a different way, and yet another way to represent functions. If you don't like linear functions, okay, and so maybe you're not interested in doing a Taylor expansion. Maybe you like Fourier functions. Maybe there are times in which you have, you're dealing with angles, you're dealing with curves and circles and spheres, and so using sines and cosines is a more natural thing, okay? And this sometimes is relevant for us because we live on planet Earth, which to a good approximation is a sphere. And so there is a way to generalize this Fourier expansion on a sphere, And sometimes when you deal with things like radiative transfer functions and stuff that we will talk about during the radiation part, well, maybe we want to think about being on a sphere. And so we'll have the generalization on the sphere of these sine and cosine functions. But again, just to give you the idea that just because I give you a function and the function is complicated, you don't have to stick to it. Maybe sometimes you can use a linear approximation. Sometimes you can write it as a sum of sines and cosines and so far. Now, are Taylor and Fourier series the only ways to write functions? Well, you probably guess no, it's not. And there are tons of other ways. You can use, if you're on a sphere, the generalization that I mentioned before is called spherical harmonics. You can use Legendre polynomials, etc., etc. You don't have to remember all this. Just keep in mind that things are very fluid when dealing with functions. Okay, and finally, the last topic. I promise that it will be a sort of a short class. The last topic that I wanted to cover today is a type of equation that you may already be familiar with, but I just wanted to go over it with you. Now, when you're in school, when you're in high school, you learn equations where, some kind of polynomial equation, a of x plus b equals to c, some simple algebraic equation like this, right? This is an equation where the unknown is a number, a real number, an integer number, a complex number, whatever. If the equation is something like this, x squared plus 1 equal to 0, then the solution is obviously the imaginary unit. And so, sometimes you have to do crazy things with your numbers, but it's always going to be a number or a value. There are equations where the unknown is a function instead of a number. And these equations, the way that these equations are defined is that they, the structure of the function is related to the function itself, okay? And these equations are called differential equations. And usually you're asked to find a particular function as a solution to these equations. We distinguish between ordinary differential equations in which you have only one independent variable, okay? And so it will be a simple case like the ones we're looking at here, f of x. And you have partial differential equations where you have more than one dimensions, and therefore things become more complicated. Now, the way these differential equations work is that you're given, for example, simple differential equations would be something like find the function whose derivative, f prime, equals to the function itself. And I give you something like, well, f at x0 equals some particular value, f0, for example. Okay. Now, this, we already discussed what this looks like and what the solution is like. But before we jump to finding the solution, this is called, by the way, this is called the Cauchy problem. I give you an ordinary differential equation, some boundary condition, and you find me the function. Okay, this is called Cauchy problem. The structure of differential equations is kind of like this. You have, I tell you how the derivatives of the function are related to the function, find me the function. The derivative of a function gives you the behavior of the function at an infinitesimal level. Remember when we looked at generic function, we said the derivative was the tangent. Was the tangent to the particular point that you're interested in. The derivative is telling you something about small changes of the function, okay? And in this case, it's telling you that the function that includes all the small changes at different points looks exactly like the function itself, okay? And this is the standard form of differential equations. Now, how do we solve this? Well, let's say f prime, we gave the definition, but what essentially f prime, what essentially was, it was, if you remember, we said the increase in the y direction that we can write down like this, the increase in the, the increase in the y direction, not the x direction. I'm sure this is completely redundant and that you know exactly what we're talking about, but just want to make sure we're on the same page. Divided by the small increase in the x direction, which was this one, okay? And this is equal to the function f, okay? And so you can multiply everything by dx and divide everything by f, and so you have dy divided by f equal, actually I think I'm just confusing you. Let me use, instead of dy, let me use the notation df. Okay. Pardon me. Df represents the infinitesimal increase in this direction. Okay, so this is df over f equals to dx. Now, we can integrate both terms. This looks like df over f. I hope you remember integrals. This looks like the logarithm of x, and this looks like, excuse me. Pardon me, I keep making mistakes. Well, I can just write it. Logarithm of f, okay? And this looks like x plus some constants that we just include in C that derive from the equation, okay? Now, you can exponentiate everything, and you would have that f of x equals to e to the c, which is another constant, let's just call it a, times e to the x. Well, but wait a minute, what is a then? Well, you can find a by using this definition, that f of x0, which by definition, by solution here, is a e to the x0. This has to be equal to f0. And so there follows that a is equal to f0 times e to the minus x0. Substitute this in, and this becomes f0 e to the x minus x0. And this is how you solve the Cauchy problem. Just to verify, when x equals to x0, this is 0, e to the 0 is 1, so this goes down, and f of x of 0 equals f0, which is exactly the requirement of the Cauchy problem. So this generally are these are sort of, this is a very simple example of what we call ordinary differential equations. Partial differential equations are kind of similar, except that you have functions that have more than one unknown. So, you might have f of x and y, okay? And in this case, your equations would involve derivatives with respect to x, but also derivatives with respect to y. So, I don't know, it could be something like the second derivative of f with respect to x plus the second derivative of f with respect to y, and this equals to something. I don't know, it could be some function g of x that the problem will specify. And while the solution of ordinary differential equation is relatively straightforward, the solution of partial differential equations is a little bit more complicated and kind of an art in of it itself. Okay, so I think we're not going to go into the PDE, partial differential equations, technicalities because it would really take a long time. And I would say that this pretty much, okay, I just wanted to give you a small example of how to solve differential equations that may be useful for sort of later in the class. Okay, now we're returning to ordinary differential equations, so much simpler to solve. In this case, we can deal with a simple function and a simple differential equation. And the differential equation is defined in this way. d of y over dx. Before I used to denote the derivative with f, but it's completely irrelevant whether you want to use f or y. It's totally okay. And you could have, for example, a function g of x here and a function h of y. This type of differential equations is called separable. And it's called separable because you can take all the functions that depend on x on one side and all the functions that depend on y on the other side. And so you'd have something like dy divided by h of y equals to g of x in dx. And you can integrate both of these. This would give you the logarithm. Well, this would give you a function h of y, and this would give you a function g of x, and you could combine the two and find the solution to this problem. Non-separable differential equations are a lot simpler. Typically f and g that are given to you are kind of simple, and so solving separable equations is not usually a big deal, but it becomes a lot harder when the equations are non-separable. And so when we have something like dy over dx plus some function p of x times y, this is one example, but it doesn't have to be this one, times q of x, okay? This is a typical example of a non-separable, let me write this down, non-separable, non-homogeneous ordinary differential equation. Okay. This equation, actually, I chose this one of all the infinitely many that I could have chosen. I chose this one because this one's going to play a role in our class. The one that we're going to deal with in particular is a little bit simpler, where this is a constant alpha. And actually, let's just go and take a look at how to solve this. So if that equals to alpha, you have dy over dx plus alpha y equals q of x. You see that this is not quite separable, right? Because if you multiply everything by dx, this gets multiplied by dx, but this also gets multiplied by dx, and you have something that depends on x and y at the same time, and you cannot tear it apart. However, just look at this element here. These two terms. It's a sum of two things, right? Now, it would be great if we could write this down somehow as as a single derivative. Okay. How do we do that? Well, one way to do it is that we could define a factor mu, and we define it like this: e to the alpha times x minus x0. Just, just because arbitrarily we defined this. And notice that this is a very interesting property, because now if you take the derivative of this, d mu, over dx, okay, it's the derivative of this stuff, but you know how to take the derivative of an exponential. That's pretty simple. That would be alpha e to the alpha x minus x0, okay, equals alpha times mu by the way we defined mu. So this is interesting. Okay, we have, this alpha mu, which kind of looks like this alpha y. So this got me thinking, what happens if we multiply both these terms by mu? And we can do that, can't we? Like, we can just do that because, if you have an equation, you multiply both terms by something, the equation is still true, right? And so this becomes mu of dy over dx plus alpha mu, which looks like something you've seen there, y. Now, just for the sake of simplicity, alpha mu is also equal to d mu dx, isn't it? And so let me just write it as d mu dx. And so this is mu times dy dx plus d mu, over dx times y. Okay, so function time derivative plus derivative time function. Mu y prime plus mu prime y. Now, what does this look like? Doesn't this look a whole lot like the product rule that we talked about at the beginning? This is exactly, in fact, the derivative of the product between mu and y with respect to x. And this was also equal to mu q of x. Now, why is this progress compared to where we were before? Well, because now you can multiply both terms by dx, okay? And you have d mu y equals to mu q, of x in dx. And you can, this is a perfect differential, so you can integrate this. This is something that only depends on x, and so you can easily integrate this. And this way, you can solve the differential equation. Now, solving the differential equation is slightly tricky. There are some caveats, not the differential equation. Solving the integral, there are some caveats in the integrals. And I'll just leave it to that. And we'll see these caveats when we'll talk about this when the time comes, when the time is right. Anyway, so this is pretty much all I had to say. So as you've seen, not much prereq to follow 620. Talked about derivatives, Taylor series, Taylor expansions, Fourier series, ordinary differential equations. We give a bunch of examples. This is pretty much all you need to know. If some of these things don't sound too familiar to you, or well, if you're not too familiar about some of these things, don't worry, nothing to worry about. Just let me know, and we can go through all of these things together individually, or we can talk about this in class some other time. This is all I had to say. Thank you so much for your attention. Let me know if this class was okay, if there's something that could have been improved. Please stay safe, and I'll see you in for the next class. Have a good day.